Massive stones weighing hundreds of tons once journeyed across continents. The ancient methods used to move them are a stunning display of human ingenuity. This video uncovers the precise quarrying strategies that made such colossal constructions possible. You will learn exactly how our ancestors mastered the art of moving the immovable, using nothing but simple tools and brilliant physics. How did they extract a single perfect block from a mountain without modern machinery? What secret techniques allowed them to glide these giants over sand and river? The answers reveal a forgotten world of engineering genius. What does it truly take to move a mountain, one stone at a time? The true secret to moving a mountain began not with force, but with a deep and patient observation of the stone itself. Ancient quarry masters understood that every type of rock has a hidden language of weakness, a natural grain and structure waiting to be read. They did not simply attack a cliff face with tools. Instead, they became detectives of the earth, searching for telltale fissures and fracture lines already written into the bedrock by millennia of geological pressure. Their first and most critical task was to listen to what the stone was telling them. A single block destined for a pyramid or a temple wall had to be flawless, and this initial selection process ensured its strength and perfection. To separate a colossal block, workers would first carve a series of small slots along an identified natural crack. Into these channels, they would insert simple, dry wooden wedges. Then they would pour water over the wood. As the wedges absorbed the moisture, they swelled with a slow, immense, and irresistible force. This gentle but powerful pressure would travel deep into the rock, coaxing the stone to split along its own preordained plane. It was a brilliant exploitation of nature's own physics, a way of convincing the mountain to give up its treasure with minimal effort and astonishing precision. This method left behind almost no wasted material, just a cleanly separated block, perfectly shaped for its epic journey. This was not brute strength. It was the birth of engineering, a silent conversation between human intellect and the ancient earth. Once the perfect block was coaxed from the mountain, a new and even greater challenge began. How do you move a stone heavier than a herd of elephants across miles of rugged terrain? The solution was as elegant as it was simple, and it started with a fundamental shift in thinking. The goal was not to lift the colossal weight, but to make it glide. Ancient engineers transformed the very ground the stone traveled on, creating a temporary road that conquered friction. They would construct pathways from specially prepared timber, laying down a smooth, lubricated track. On this wooden road, they placed a sledge, a massive wooden platform that cradled the stone. Teams of workers or oxen would then pull ropes attached to the sledge, sliding the immense block forward. But the true secret, the element that made this Herculean task possible, was the application of a liquid. Water was poured liberally onto the wooden track in front of the moving sledge. This water acted as a powerful lubricant, drastically reducing the friction between the wooden sledge and the wooden path. Evidence from ancient depictions and modern experiments shows that wetting the track could reduce the pulling force required by as much as half. This was not about raw muscle, but about outsmarting physics itself. Can you picture the scene, the slow, steady procession of a monument in motion, gliding on a river of human ingenuity? This method of the lubricated sledge was a triumph of practical physics, turning an impossible drag into a manageable, rhythmic pull. It proved that the greatest force in moving mountains was not strength alone, but the clever application of a simple, abundant resource. Water and wood became the unsung heroes that delivered stone giants to their final, majestic resting places. But for stone like granite, a material that laughs at simple wedges, a more dramatic method was required. When faced with a cliff of unyielding rock, ancient engineers turned to one of humanity's oldest tools, fire. They would build controlled, hot fires directly against the granite surface. The intense heat would cause the outer layer of the stone to expand rapidly, creating immense stress within the rock. Then, at the peak of this thermal pressure, workers would douse the flames with torrents of water. The sudden, violent cooling made the superheated rock contract in an instant. This shocking temperature change, known as thermal shock, created a network of microfractures, causing the granite to crack and split along controlled lines. It was a brilliant act of forcing the stone to break itself from the inside out. This technique, fire setting, transformed a seemingly impossible task into a manageable one. You can see its legacy in Roman quarries and the breathtaking stonework of the Inca, where massive blocks were pried from the earth using nothing but strategic temperature manipulation. It was a raw demonstration of physics, a way to make the mountain itself do the hard work of breaking apart. Yet for the truly colossal stones, a different kind of patience was required, one that involved carving directly into the living rock. In places like the ancient quarries of Balbeck, we find the ultimate expression of this approach, a method known as precision channeling. Here, workers did not wait for the stone to split. Instead, they meticulously defined the block they wanted by carving deep, narrow trenches completely around it, isolating a single giant from the mountain. This was a monumental undertaking in itself, achieved with nothing more than stone hammers and metal chisels. For months or even years, teams of workers would chip away, inch by painstaking inch, creating a deep moat in the solid stone. This trench served a brilliant dual purpose. It not only outlined the block with perfect precision, but it also created the working space needed for the final, most delicate act, the undercutting. Once the channels were deep enough, workers would crawl beneath the isolated block. Lying on their backs in the cramped, dark space, they would carefully chisel away the remaining bedrock that still supported the colossal weight above them. This was work that demanded incredible skill and courage, removing the very foundation of the stone piece by piece. The final step was the insertion of levers or lifting devices into the newly created gaps. With a coordinated push, they could coax the freed monolith upward, ready for its journey. This entire process was a testament to a different kind of genius, not the clever physics of fire or water, but the profound power of foresight and meticulous planning. It was a slow, deliberate dance with the mountain, ensuring that when the stone was finally moved, it was already a masterpiece of engineering, perfectly formed and perfectly intact. For the hardest stones where fire and wedges could not gain a foothold, quarry masters turned to a strategy of pure persistence. They engaged in a slow, rhythmic conversation with the granite, using tools made from a stone even harder than their target. Dolerite, a dense and incredibly tough igneous rock, was shaped into heavy, fist-sized pounders. A worker's task was not to split the stone with a single blow, but to gradually, methodically pulverize it. They would strike the same spot on the granite surface again and again and again. Each impact from the dolerite pounder would shatter a tiny, almost invisible fragment of the quartz crystals within the granite. This was a battle of attrition, fought one microscopic grain at a time. Over days and weeks of relentless, careful pounding, a shallow groove would begin to form. Teams of workers would stand side by side, their synchronized strikes creating a controlled channel, slowly deepening it until it reached the desired depth. This was not a quick process. To free a single large block could require millions of precise strikes, a testament to an almost unimaginable level of human endurance and coordination. The sound of the quarry would have been a constant percussive rhythm, the heartbeat of a civilization patiently carving its legacy from the living rock. We can still see the evidence of this painstaking work in the ancient quarries of Aswan in Egypt, where the unfinished obelisk remains partly attached to the bedrock, its surface covered in the very grooves created by these stone tools. This method reveals a different facet of ancient genius. It was not always about clever physics or exploiting natural weaknesses. Sometimes the greatest innovation was the sheer organizational power to coordinate a workforce, to maintain the rhythm and precision required for years on end, transforming an entire mountainside into a city of stone through the cumulative power of countless careful strikes. While some quarries echoed with the rhythmic strikes of stone on stone, others transformed into temporary, shallow lakes. In the river valleys of Mesopotamia, engineers mastered a fifth strategy, one that turned water from a simple lubricant into a powerful lifting force. They learned to command the very flow of rivers to do their heaviest work. The process began with the careful partial detachment of a massive stone block, undercut just enough to be freed but still resting securely in its bedrock cradle. Then workers would divert water from a nearby source, deliberately flooding the entire quarry pit. As the water level rose, it would gradually surround the stone. This was where the principle of buoyancy came into play. The rising water would exert an upward pressure on the block, effectively reducing its weight and counteracting the immense grip of gravity. The stone, now far lighter in the water, could be more easily shifted or tilted onto a waiting raft of logs or bundled reeds. Once securely afloat, the block was no longer a dead weight to be dragged. It became a cargo that could be poled or guided with ropes across the submerged quarry floor. This method created a seamless bridge between extraction and travel. A stone could be floated directly from its birthplace in the quarry into a prepared canal, beginning its journey to a distant construction site without ever needing to be lifted onto a sledge. This was logistics reimagined through the lens of hydrodynamics. Why struggle to move a mountain over land when you could convince the mountain to float? This brilliant integration of quarrying and transportation reveals a holistic way of thinking, where the challenge was not seen as a series of separate problems, but as a single, fluid process to be solved with the most abundant and manageable resource available, water itself. Even with water lifting a stone or a sledge ready to glide, the first motion was always the most difficult. That initial shift from stillness, breaking the immense grip of inertia, required a force that was both powerful and coordinated. This is where the true scale of ancient logistics came to life, a symphony of muscle and management. The primary source of this sustained power came from domesticated animals, particularly oxen. These patient, powerful creatures were the engines of the ancient world, capable of pulling for hours on end with a steady, relentless force that human muscles alone could not match. Teams of oxen, sometimes numbering in the dozens for a single stone, would be harnessed with ropes to the waiting sledge, but before they could pull, the ground itself had to be prepared. Workers would place a path of wooden rollers, often freshly cut tree trunks, directly in front of the sledge. As the oxen strained and the pullers chanted in rhythm, the colossal stone would lurch forward, its weight now borne by the rolling logs beneath it. This was a brilliant, dynamic system. As the sledge moved over a roller, workers at the back would frantically retrieve the freed logs and run them to the front, creating a continuous, moving track. Can you hear the sounds of that operation, the deep groaning of the ropes, the shouts of the team coordinating the rollers, the slow, grinding creak of a multi-ton block inching its way forward? This was not just about raw strength, it was about perfect timing and social organization. Every person, from the ox driver to the roller boy, had a role that was essential to the whole. This collaborative effort underscores a fundamental truth behind these engineering marvels. The greatest resource was not just wood or water, but the coordinated will of an entire community, harnessed to achieve a single, seemingly impossible goal. The true genius of ancient engineering lies in its elegant simplicity. While massive teams and complex logistics were essential, the most transformative innovation was often a single, brilliantly designed tool. Enter the sledge, a deceptively simple wooden platform that fundamentally changed humanity's relationship with weight and distance. This was not merely a slab of wood, it was a carefully crafted device engineered to conquer friction. By placing a multi-ton stone onto a sledge, builders dramatically reduced its contact with the ground. Instead of dragging a rough, uneven base across the earth, the stone now rested on a smooth, polished wooden surface. This alone made movement easier, but the ancient engineers did not stop there. They turned the very ground into a partner in the process. Tomb paintings from ancient Egypt show a vivid detail, a worker pouring water onto the track directly in front of the moving sledge. This was the masterstroke. The water, or sometimes a slick mixture of mud, acted as a powerful lubricant between the sledge's runners and the prepared pathway. It created a thin, slippery film that transformed a bone-jarring drag into a surprisingly smooth glide. Modern experiments have proven the stunning efficiency of this method. A team of people can pull a 1-ton stone on a dry sledge with great difficulty, but that same team can effortlessly move a stone weighing several tons once the path is wet. This lubricated sledge system unlocked architectural possibilities that were previously unimaginable. It meant that a perfectly quarried block from a distant site was no longer trapped by its own mass. It could now journey across flat plains and gentle slopes, traversing the gap between the lonely quarry and the rising monument. This incremental innovation, this marriage of wood and water, did not just move stone. It moved civilization forward, one sliding block at a time. Yet for all the power of the sledge, another system offered an even more fluid form of motion, one that mimicked the wheel itself. This was the realm of the roller system, a brilliant application of cylindrical motion to conquer friction on a grand scale. The principle was simple in its genius. By placing a series of sturdy logs, often freshly cut tree trunks, perpendicular to the path of travel, workers transformed a difficult drag into a smooth, rolling advance. As a colossal stone on its sledge was pulled forward, it would ride up onto these cylindrical rollers. The key physics at play was the conversion of sliding friction into rolling friction, a change that could reduce the required pulling force by an astonishing 80% or more. The immense weight was no longer scraping against a static path, but was instead carried by the rotating logs. This created a dynamic, moving road that traveled with the load. The process, however, demanded perfect coordination. As the sledge moved forward and a roller emerged from the back, a team of workers would quickly retrieve it and dash to the front to place it back into the path. This continuous cycle created a perpetual pathway, a treadmill of wood that allowed a stone to walk itself across the landscape. Can you envision the rhythm of this operation, the constant, rolling motion under the stone, the synchronized dance of the workers as they kept the wooden track alive? This method is powerfully theorized for the transport of Stonehenge's famous bluestones, which journeyed over 150 miles from their Welsh quarry. The use of rollers would have made such an epic overland trek not just possible but practical. It represents a foundational mastery of physics, achieved not through complex equations, but through relentless observation and practical problem solving. They learned that by making the earth itself roll, they could make the mountains move. Even the most perfectly gliding sledge met its match at a steep incline or a construction site's foundation. How do you lift a 100-ton block onto a rising pyramid wall? The answer was found not in raw power, but in the elegant principle of leverage. Ancient engineers mastered the art of mechanical advantage, using long, sturdy wooden beams as levers. The secret was the pivot point, a solid stone known as a fulcrum. By placing this fulcrum very close to the massive stone, a team of workers applying force to the long end of the beam could generate an astonishing upward lift. The longer the lever, the greater the force they could exert with the same amount of effort. It was physics made tangible, a way to make a small human push move a weight that defied direct lifting. But for truly massive stones, even a long lever had its limits. This is where a second principle came into play, the ingenious use of counterweights. Instead of relying solely on human muscle pulling down on the lever, engineers would hang heavy weights like bags of sand or smaller stones from the long end of the beam. This counterweight provided a constant, reliable force, allowing the team to make incremental, controlled lifts. They would raise the stone just a little, slide wooden cribbing or stone blocks underneath to support it, then reset the lever and counterweight to lift it again. This patient step-by-step process, known as walking the stone upward, prevented any sudden, dangerous shifts. You can see the legacy of this method in the precise stonework of Greek temples and Roman aqueducts, where massive blocks were carefully set into place high above the ground. It was a system that traded speed for absolute control, ensuring that a single block, representing years of quarrying and transport, was positioned with perfect accuracy. This marriage of the lever and counterweight transformed the vertical plane from an insurmountable barrier into just another manageable step in the journey from quarry to monument. The final ascent was perhaps the most daunting challenge of all. After a stone had journeyed for miles, it faced its ultimate test, the climb to its permanent place high on a pyramid or temple wall. The solution was as monumental as the goal itself, a temporary mountain built to conquer the real one. Ancient engineers constructed colossal ramps made of earth, brick, and rubble, creating a gently sloping highway that reached from the ground to the very top of the rising structure. This was the practical application of the inclined plane, one of humanity's most fundamental mechanical discoveries. By extending the distance of the climb, the ramp dramatically reduced the steepness of the angle. This meant that at any given moment, the force required to pull the stone upward was only a fraction of its total, crushing weight. It transformed an impossible vertical lift into a long but manageable horizontal drag. Teams of workers or oxen could pull a sledge bearing a multi-ton block up this earthen highway, their effort distributed over the entire length of the journey. For structures like the Great Pyramid, these ramps were not simple straight shots. Evidence suggests they may have spiraled around the growing edifice, a continuous roadway that allowed for a constant supply of stones to be delivered to every rising course. The construction of the ramp itself was a feat of logistics, requiring as much material and labor as the inner core of the pyramid. This reveals a profound understanding of trade-offs. The immense work of building and later dismantling the ramp was worth it, because it made the impossible act of lifting stones hundreds of feet into the air a matter of simple, coordinated pulling. This method stands as a perfect symbol of ancient engineering philosophy, where patience and long-term planning always triumphed over brute force. It was not about a single, heroic effort, but about creating a system where sustained, collective labor could achieve a miracle, one slow, steady pull at a time. Far from the organized quarries of empires, another ancient mystery took shape, this time in the jungles of Costa Rica. Here, a unique culture mastered the art of perfection in stone, creating enormous, flawlessly round spheres. Some of these polished granite balls weigh more than 15 tons, and their journey from raw rock to polished globe is a puzzle that captivates archaeologists. How do you transport a perfect sphere over miles of dense rainforest and uneven ground? A round shape, while easy to roll, is notoriously difficult to steer and control, especially when its weight is colossal. The prevailing theory suggests a multi-step solution, a blend of the methods we have already explored. It is likely these spheres were moved using a combination of earthen ramps and wooden rollers. But the true innovation may have been a specially designed cradle or wooden frame that encased the sphere. This frame would have transformed the unpredictable ball into a stable, manageable load. Think of it like placing a bowling ball inside a snug box. Suddenly you can lift and carry it without it rolling away. This cradle could have been then placed on top of rollers, allowing teams to pull it along a prepared path while the frame kept the sphere from veering off course. Levers would have been essential for the delicate work of loading the sphere into its frame and for making minor adjustments during the journey. These stone spheres stand as a powerful testament to the diversity of ancient problem solving. They were not building pyramids with rectangular blocks, but they faced the same fundamental challenge of mass and distance. Their solution highlights a universal truth: every culture, faced with an immovable object, found a way to make it move by observing the world around them and applying brilliant practical physics. The perfect spheres of Costa Rica are more than artifacts. They are monuments to human adaptability, proving that the principles of engineering could be shaped to fit any form, even a perfect circle. The silent glide of a barge on a river is a world away from the grinding drag of a sledge. For ancient engineers, a flowing waterway was not a barrier but a superhighway, a natural conveyor belt that could carry the heaviest stones with an ease that land travel could never match. The most iconic example of this is the journey of the granite blocks for the pyramids at Giza. Their story began over 500 miles to the south in the Quarries of Aswan. There, colossal blocks were carefully loaded onto massive, purpose-built wooden barges. Once secured, the current of the Nile itself became the primary engine. The river's steady, predictable flow northward toward the Mediterranean meant that for a significant portion of the journey, the barge and its multi-ton cargo were simply carried by the water. For upstream travel or precise maneuvering, teams of rowers or men pulling from towpaths on the riverbank provided the necessary guidance and additional power. This method fundamentally transformed the economics of scale. Moving a 200-ton obelisk by land would have been a logistical nightmare requiring thousands of workers and months of labor. On the water, that same obelisk became a manageable cargo, its weight effortlessly supported by the buoyant force of its vessel. The challenge then shifted from pulling to balancing, from conquering friction to mastering stability. The boats themselves were feats of engineering, designed with a wide, flat-bottomed hull to distribute the immense load and prevent capsizing. This strategic use of river transport effectively turned the landscape inside out. A distant quarry was no longer distant if a river connected it to the building site. It expanded the possible sourcing of materials from a few local miles to hundreds of miles inland, allowing architects to select the perfect stone for their vision, regardless of where it was born. The river did not just move stone, it connected an empire, making the impossible not just possible, but elegantly, quietly efficient. The final placement of a stone was often the most delicate part of the entire journey. After traveling for miles, a colossal block had to be set into its exact position, sometimes within a fraction of an inch. In the tight confines of a rising Mesoamerican temple, there was no room for a team of oxen or a long ramp. This is where a 13th strategy, one of brilliant finesse, came into play. Evidence from ancient sites points to the use of specialized wooden cradles. These were not simple platforms, but custom-built frames designed to encase a stone completely. The genius of this device lay in its ability to transform a static, immovable mass into something that could be manipulated. With a stone securely held in its wooden embrace, workers could use levers to rock the entire assembly back and forth. This rocking motion created a semi-rotational pivot, a way to inch the stone forward or sideways with a surprising degree of control. Think of how you might adjust a heavy piece of furniture in your home. You do not lift it, you tilt and pivot one corner at a time to walk it across the floor. Ancient builders scaled this simple principle to a monumental level. The cradle acted as a mechanical intermediary, distributing the strain and allowing a small team to achieve what would otherwise require an army. It was the perfect tool for the final act, for navigating a narrow corridor or aligning a massive lintel over a doorway with painstaking precision. This technique reveals a profound understanding that the challenge was not always about raw power. Sometimes the ultimate innovation was a tool that granted control, turning the final, back-breaking shove into a series of manageable, calculated movements. While the deserts of Egypt relied on water and wood, the frozen north discovered a different kind of slippery surface. In the harsh Scandinavian winters, Norse builders turned the biting cold from an obstacle into their greatest ally. They mastered the art of ice roads, creating temporary superhighways for stone. The method was brilliantly straightforward. Workers would pour water onto a prepared pathway during freezing conditions. Layer by layer, the water would solidify into a hard, incredibly slick sheet of ice. A stone resting on a sledge when pulled across this frozen track encountered almost no friction. The ice provided a surface so smooth that the force needed to initiate movement was slashed to a tiny fraction of what was required on bare ground. This was not a mere convenience, it was a complete reimagining of the landscape. The long, dark winters, which halted most other construction, became the ideal season for transporting the heaviest materials. A task that might take 100 workers in the summer could be accomplished by a small team and a few oxen on a perfectly glazed ice path. This environmental adaptation speaks to a deeper truth about ancient innovation. It was never a one-size-fits-all formula. True genius lay in observing the local world and asking how its unique characteristics could be harnessed. The Norse did not fight their climate, they partnered with it, using the very essence of winter to slide their legacy into place. Even the most perfectly built sledge could drift off course without a guiding hand. For directional control over these multi-ton loads, ancient engineers turned to the humble rope, transforming it into a precise instrument of navigation. While complex pulley systems with multiple wheels were a later innovation, the simple rope itself was a marvel of applied physics. Teams of pullers were not just a source of raw power, they were the steering mechanism. By positioning teams on either side of the sledge and attaching ropes at strategic points, they could exert subtle but decisive influence on its path. A coordinated pull from the left would nudge the massive block to the right, and vice versa. This was not about brute force, but about coordinated finesse. Assyrian stone reliefs vividly depict this organized chaos, showing lines of workers straining on ropes, their bodies leaning in unison to guide colossal stone statues toward a palace gateway. The true key to this method was not the rope itself, but the human rhythm behind it. This required flawless communication, likely through chants or drumbeats that synchronized every individual tug into a single, unified directional force. Can you hear the rhythmic calls echoing across the plain? A human metronome ensuring that 100 separate efforts became one controlled motion. This system of collective guidance reveals that ancient logistics were as much about social organization as they were about physics. It was a living network of communication where every puller was a vital neuron in the brain that guided a stone giant home. The immense stones were more than just building materials, they were vessels of meaning. Across many ancient cultures, the act of quarrying was not merely a technical operation. It was a sacred dialogue with the earth itself. The site where stone was extracted was often considered a living, spiritual landscape, a place where the boundary between the human world and the divine grew thin. Before a single tool ever touched the rock, rituals were performed to honor the mountain and seek permission from the forces believed to dwell within it. Offerings of food, precious objects, or ceremonial liquids were common, a gesture of respect and a plea for safe passage for both the workers and the stone they intended to remove. This was not superstition, it was a foundational part of the engineering process, ensuring that the project was aligned with a greater cosmic order. For the Inca, this belief was particularly profound. They understood the world as being animated by a vital force, and certain stones, or huacas, were seen as especially powerful vessels of this energy. To quarry such a stone was not to conquer nature, but to invite a piece of that sacred power to join a new human creation, like a temple or a royal estate. The quarrying process itself became a ceremonial act, a careful extraction that maintained the stone's spiritual integrity. The rhythmic strikes of stone tools were not just noise, they were part of a ritual cadence, a physical prayer that connected the labor of human hands to the cycles of the sun, the moon, and the earth. This spiritual dimension transforms our understanding of these ancient sites. They were not just open-air factories, they were outdoor cathedrals where practical skill and profound belief were woven together into a single, unified effort. The true foundation of a pyramid or a great wall was not just its first layer of stone, but the layer of meaning and reverence laid down at the very moment of its birth in the quarry. The Roman Empire transformed quarrying from a local craft into a continent-spanning industry. They viewed stone not just as a material, but as the lifeblood of their civilization, and they built a circulatory system to pump it across their entire domain. This was the 17th strategy, a logistical revolution built on two foundational pillars, the industrial quarry and the indestructible road. Roman quarries were models of systematic extraction, operating with a military-like precision that produced blocks in standardized sizes. This allowed for interchangeable parts on a monumental scale, where a stone cut in a quarry in North Africa could fit perfectly into a wall being erected in Britain. But the true genius lay in what connected these distant points. The Romans constructed a vast network of roads, engineering marvels built in layers with deep foundations and durable surfaces. These were not simple dirt paths, they were reinforced highways capable of supporting incredible weights year-round. Specially designed carts with wide, iron-rimmed wheels were commissioned to carry the quarried stone. A single, massive block could be loaded onto one of these heavy-duty vehicles and then begin a steady, reliable journey overland. The efficiency of this system was breathtaking. It meant that a city's growth was no longer limited by the local availability of building stone. A provincial capital could now source its marble from hundreds of miles away, its forum and temples clad in the same fine materials as those in the heart of Rome itself. This integration of standardized extraction with purpose-built transport created a logistical framework that powered urban expansion for centuries. The very stones of the empire became mobile ambassadors of Roman order, traveling on roads that were not just pathways for legions, but the supply lines for an entire civilization's architectural ambition. Long before empires built with standardized stone, prehistoric Europe was already moving mountains. Across the misty landscapes of places like Karnak and Avebury, communities came together to undertake a task that defined their very identity, the transport of megaliths. These colossal stones were not hauled by slaves under a whip, but by free people united in a common, monumental goal. The engineering was brilliantly straightforward, yet profound in its social implications. During seasonal gatherings, when the community was at its largest, they would construct pathways of timber and earth, greasing the tracks with animal fat or water to create a slick surface. Teams would then take hold of long ropes made of plant fiber or leather, and with a coordinated heave, begin the slow, rhythmic drag of the stone. The sound would have been a chorus of straining ropes, rhythmic chants, and the steady slide of stone on wood, a symphony of collective effort. This was more than just construction, it was a powerful ritual of social bonding. The shared hardship and the ultimate triumph of seeing a stone settle into its sacred place reinforced the bonds of kinship and collective identity. Every successful pull was a reminder that they were stronger together. The true purpose of moving these megaliths may have been as much about building community as it was about building monuments. The finished stone circle was not just an astronomical calendar or a temple. It was a permanent testament to the fact that this society could achieve the impossible, not through the command of a king, but through the woven strength of every willing pair of hands. The rhythm of the ancient quarry was not just a matter of tools and manpower, but a profound dance with the seasons themselves. Master builders understood that to fight the climate was to invite failure, so they instead learned its tempo and planned their monumental work accordingly. The entire logistics chain, from extraction to final placement, was scheduled around the annual weather patterns. In regions with distinct wet and dry seasons, the most intensive transport operations were reserved for the long, rainless months. A pathway that was a sun-baked, solid surface in the dry season could transform into a bottomless quagmire with the first heavy rains, trapping a multi-ton sledge in impassable mud. By waiting for the dry period, they ensured the ground was firm and predictable, turning the very earth into a reliable partner. This was not a passive waiting game, it was an active and strategic scheduling of resources. Quarrying might continue year-round in some areas, with blocks stockpiled near the quarry face, ready for the great push of transport when conditions were perfect. In colder northern climates, a different seasonal ally emerged: the deep freeze of winter. Ground that was soft and yielding in the summer would be transformed by sustained frost into a surface as hard as stone. This natural paving allowed for the movement of colossal loads with unprecedented stability, as the frozen earth could not rut or collapse under the immense pressure. This careful timing reveals a layer of genius beyond levers and sledges. It was an understanding that the greatest engineering project is one that works in harmony with the natural world, not against it. The true blueprint for moving a mountain was written in the cycles of the sun and the patterns of the stars, a calendar of stone that dictated when to carve, when to wait, and when to make the earth itself carry its own weight forward. These abandoned quarries are silent libraries of ancient engineering. At sites like Mount Sipylus in Turkey, the story is not told in completed monuments, but in the very rock left behind. Here you can walk among the ghosts of half-finished projects where tool marks are frozen in time, waiting to reveal their secrets. The most telling clues are the failures, the blocks that cracked in the wrong place or were abandoned mid-extraction. A deep, irregular fissure in a granite slab speaks volumes about a miscalculation with fire setting, a lesson learned the hard way. The precise channels carved around a block that was never freed show the incredible investment of time and labor that was sometimes willingly written off when a flaw was discovered. These sites are open-air laboratories, offering a raw, unfiltered look at the process of trial and error. We see how quarry masters experimented with different techniques on the same rock face, adapting their approach based on the stone's unique character. This evidence dismantles the myth of seamless, effortless ancient genius. It reveals a reality of persistent problem-solving, where each failed attempt was a data point that refined the next. The true masterpiece was not the single perfect block, but the accumulated knowledge carved directly into the mountain itself that made all future miracles possible. The true efficiency of ancient construction lay in a brilliant act of foresight, reshaping the stone long before it reached its final home. Quarry masters understood that every pound of unnecessary rock left on a block was a burden to be hauled for miles. So they began the sculpting process right at the source, transforming a raw, jagged monolith into a roughly finished shape. This was not crude hacking, but a careful calculation of volume and form. By skillfully removing excess material at the quarry, they dramatically reduced the block's weight, making the ensuing journey over rollers or sledges immeasurably easier. This practice reveals a sophisticated understanding of the entire building pipeline, where the first cut was made with the final destination in mind. The Romans elevated this concept to an industrial art. Their quarries produced blocks in standardized dimensions, creating a kind of modular system in stone. A block cut in a quarry in Spain would have the same proportional dimensions as one from Greece, allowing them to fit together seamlessly in a wall being built in Gaul. This consistency meant that the builders at the construction site did not waste precious time and effort reshaping stones to make them fit. They could rely on the precision already engineered into the material itself. The intricate dovetailed joints and interlocking shapes found in Inca walls are a breathtaking testament to this same principle of pre-planning. Each stone was uniquely shaped at the quarry to complement its neighbors, a monumental three-dimensional puzzle solved before the first piece ever left the mountain. This mathematical precision in initial shaping was a quiet revolution in logistics. It shifted the most complex work to the beginning of the process, where space and resources were abundant, ensuring that the final act of construction was not a struggle of brute force, but a smooth, almost graceful assembly of perfectly prepared components. The true power behind these ancient quarries was not just the strength of their tools, but the reach of their trade routes. Across the vast networks of the ancient world, ideas traveled alongside spices and silks. Knowledge of quarrying and transport became a highly valued commodity, passed from one civilization to the next through merchants and artisans. The Phoenicians, master sailors of the Mediterranean, likely acted as key conduits for this exchange. As they established trading posts from Lebanon to Spain, they did not just carry goods, they carried techniques. A method for shaping limestone perfected in one port city could be shared in another, where it would be adapted to the local granite or sandstone. This was not a simple copy and paste of technology. It was a process of creative adaptation, a cross-pollination that led to hybrid innovations. A lifting device from Egypt might be combined with a local sled design in Greece, creating a new, more efficient system for moving blocks up a steep acropolis. This constant sharing and refinement accelerated progress at an incredible rate. A breakthrough that might have taken one culture centuries to develop in isolation could now spread across continents in a generation. The stone giants of the ancient world stand not as isolated achievements, but as monuments to a connected world where human ingenuity was a shared resource, flowing along the same paths that carried the dreams of empires. The legacy of ancient quarries extends far beyond the monuments they built. While these operations permanently reshaped the earth, their approach often reflected a surprising foresight, balancing immense need with a form of early environmental stewardship. We tend to picture these sites as barren wastelands, but many were actively used and reused for centuries, even millennia. This long-term perspective transformed what could have been pure extraction into a cycle of resourcefulness. The waste material, the smaller fragments and chips of stone left over from carving the great blocks, was rarely discarded. Instead, it was gathered and repurposed as fill for building foundations, aggregate for roadbeds, or raw material for everyday tools and smaller structures. Nothing was truly wasted. In a remarkable act of landscape reclamation, some quarry pits were given entirely new lives long after the last block was removed. A deep excavation that had supplied stone for a city's walls might later be carefully lined and converted into a vital reservoir, capturing precious rainwater for the community. Other pits were gradually transformed into lush, terraced gardens, their sheltered microclimates perfect for cultivation. This practice reveals a profound understanding that a resource site could have multiple purposes across generations. The quarry was not just a hole in the ground to be abandoned, but a part of the living landscape, a place whose value could evolve from extraction to sustenance. This long-term perspective challenges our modern assumptions, showing that grand-scale projects and a respectful relationship with the environment were not always in conflict. The true monument was not just the temple that rose from the stone, but the enduring, adaptable wisdom that ensured the land itself could continue to provide long after the builders were gone. A single block of stone is inert, its potential locked away until human hands and minds awaken it. The real magic of these ancient sites did not reside in the tools or the techniques alone, but in the generations of unsung masters who wielded them. These were the quarry engineers, the sledge captains, and the rope teams, individuals whose names are lost to history, but whose collective genius is etched into every finished monument. They possessed a kind of living library of knowledge, an intuitive grasp of physics passed from elder to apprentice through demonstration and shared experience. They knew precisely how much water would make the wooden wedges swell just enough to split granite without shattering it. They could judge the exact consistency of mud needed to lubricate a sledge path for a specific type of stone. This was not knowledge written in books, but a deep, tactile understanding of materials and forces, learned over a lifetime of patient observation. The coordination required was a marvel of social organization. An overseer standing on a high rock did not just shout orders, he read the rhythm of the entire operation. He watched the strain on the ropes, the placement of the rollers, the synchronized breathing of the pullers, directing this human machine with an almost musical precision. Can you hear the chorus of their efforts, the rhythmic chants that kept 100 pullers in perfect time, the unified heave that turned individual strength into a single, unstoppable force? These projects were triumphs of community, where the shared goal of creating something lasting for their people fueled a determination that no single person could muster alone. They moved mountains not by magic, but by the accumulated wisdom of centuries, a legacy of skill and solidarity that remains the true, unshakable foundation of every stone they ever set in place. The silent genius of ancient quarries is now being tested in the open air by modern hands. Researchers in the field of experimental archaeology are dedicating themselves to a profound challenge: to rebuild the past using only the tools and materials that would have been available thousands of years ago. They construct massive wooden sledges, carefully shape stone rollers, and mix lubricants from water and local clay, all in an effort to answer one persistent question. Could it really have been done this way? The most telling experiments involve Egyptian obelisks, those towering stone needles that seem to defy the very logic of movement. In one famous trial, a team attempted to transport a newly carved 35-ton obelisk using a replica wooden barge and a system of canals. The project was a stunning success, proving that such a monument could be floated and guided with remarkable control. Yet the experiment revealed something even more valuable than a simple yes or no. It laid bare the sheer human dimension of the task. The coordination required was immense, with teams of volunteers needing to act as a single organism, their movements synchronized to the rhythm of shouted command. Every step was a lesson in logistics, from the initial groaning effort to get the sledge moving to the careful, constant repositioning of the log rollers. These reconstructions do more than validate theories, they breathe life into them. They transform abstract concepts of physics and engineering into the tangible strain on a rope, the smell of wet wood, and the shared triumph of seeing a stone slide forward just one more inch. This hands-on research closes the gap between our world and theirs, offering us not just a blueprint of how it was done, but a fleeting, powerful glimpse into the sweat, the rhythm, and the collective spirit that truly moved these mountains. Even with all we have uncovered, some ancient stones guard their journeys with an obstinate silence. Across the globe, certain megalithic puzzles remain just that, their solutions lost to time and inspiring fierce debate among researchers. On the remote expanse of Easter Island, the iconic Moai statues stand with their backs to the sea, but how they traversed many miles from the quarry to the coast is a question that divides experts. One compelling theory suggests a rocking, walking motion, where teams used ropes to sway the massive figures from side to side, effectively making them walk forward in a slow, deliberate shuffle. Yet another hypothesis proposes a simpler method of dragging them on a lubricated path, not unlike the sledges of Egypt. The truth may be a combination of techniques adapted to the island's unique landscape and resources. Similarly, the capstones of European dolmens, those massive table-like structures, present a different kind of mystery. We understand the principles of levers and ramps, but the precise social organization and the clever, perhaps temporary, wooden structures used to lift and balance these multi-ton slabs onto their uprights remain largely in the realm of educated speculation. These are not failures of archaeology, but rather invitations. They remind us that the past is not a fully solved equation. Each unanswered question is a spark for new generations of explorers, a testament that the story of human ingenuity is still being written, one rediscovered secret at a time. From the fire-setting quarries of antiquity to the sledges that glided over desert sands, the story of moving immense stones is a profound testament to human creativity and collaboration. These were not the acts of a lone genius, but the symphony of entire communities, where every rope puller and water carrier played a vital role in a shared, monumental goal. The legacy they left behind is written in the silent, enduring stone of pyramids, temples, and circles that still capture our breath today. But their true gift was not just the monuments themselves. It was the foundational principles they discovered, the elegant physics of the lever, the roller, and the lubricated path, which laid the essential groundwork for the modern engineering that shapes our world. As we face our own immense challenges in sustainable design and construction, these ancient methods offer a powerful inspiration. They remind us that the most elegant solutions are often born from observing the natural world and working in harmony with its forces, not fighting against them with brute strength. The patience, the planning, and the profound respect for material and environment demonstrated in these quarries are lessons that resonate more strongly than ever. Thank you for joining this exploration into how our ancestors moved mountains. We would love to hear which quarrying strategy amazed you the most in the comments below. And if you enjoyed this journey, subscribe for more mysteries of history.